Finally, how can further research and advanced material synthesis strategies address the current limitations observed in both NaFeO2 and NaFePO4 cathodes to optimize their electrochemical performance for next-generation sodium-ion battery applications? How is olivine-type NaFePO4 obtained by ion exchange with LiFePO4, and in what ways does the greater complexity of the synthesis process influence its structural and electrochemical properties? How does the formation of an ordered phase of sodium ions during the discharge process lead to the appearance of two distinct discharge platforms in olivine-type NaFePO4, and what mechanisms underlie this behavior? Can Davis Stearns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What significance does the early research finding that olivine-type NaFePO4 can deliver a discharge-specific capacity of 120 mAh G superscript 1 at a working voltage of 2.8 V have in terms of assessing its performance, and how is this capacity precisely measured? How does the material's ability to retain 90% of its capacity over 100 cycles at a current density of 0.1 C reflect on its stability and potential longevity as a cathode? In what manner do batteries with aqueous electrolytes enhance the overall electrochemical performance of olivine-type NaFePO4 compared to those using organic electrolytes, and which specific properties of the aqueous system, such as improved ionic conductivity and lower interface impedance, are responsible for this improvement? How do the charge and discharge curves presented in figures 3.31 C and D demonstrate that when the voltage range in the organic system is matched to the stable range observed in water-based systems, the polarization and rate characteristics of NaFePO4 are significantly improved, and what insights does this comparison provide? Finally, considering all these factors, why does olivine-type NaFePO4 appear to be more suitable as a cathode material for aqueous sodium-ion batteries? And what further research or modifications could be pursued to optimize its performance even more in such systems? How does the structural diagram of NaFePO4, as shown in parts A and B, illustrate the differences between the olivine-type NaFePO4 and the sodium phosphate-type NaFePO4, and what key features such as lattice arrangement, ion conduction channels, and the coordination environment of the constituent atoms can be identified from these diagrams? How do these structural differences potentially influence the electrochemical behavior of the material, and in what ways might the formation of distinct crystalline phases affect the pathways for sodium-ion transport? How do the electrochemical property diagrams in parts C and D depict the performance of olivine-type NaFePO4 in different electrolyte systems, and what variations in capacity, rate performance, and polarization are evident when comparing organic versus aqueous electrolytes? What?